we're going to do the second part of the power hardware in the loop presentation. I'm going to do a small introduction again for those who weren't there this morning for the extents presentation. So basically, what is the power hardware in the loop? What makes it different from classic hardware in the loop simulation? Basically, it is that you exchange power between the amplifier and the real hardware. So, like we can see in the schematic, we have on the complete left the host workstation, which controls the simulation on the target computer. Then, from the target computer, you can control signals going through the amplifier to connect with real hardware. Afterwards, the results that are taken from the real hardware through sensors are re-injected back in the simulator, where the equipment results can be taken into account in the model. So here we can see the advantage of using these different equipment for PHIL. So for the real-time simulator, we take advantage of the great computing capabilities of the target in order to be able to simulate power system, power electronics, protection equipments, control logic, and so on. In order to achieve a proper connection with hardware, we need to make sure to have a high-quality amplifier, which permits good accuracy, a low distortion, a high bandwidth, and any other parameters that is relevant for your hardware in the loop simulation. And in terms of real hardware that can be connected to the simulator, we're talking about a variety of items that can, among those, we have the wind turbine, the solar panels, motors, generators, protection relays. So we can see that there's a lot of potential application for the PHIL. We have grid application, motor application, aerospace, military, automotive, transportation. So it's only a matter of knowing what you want to test. Then in terms of OPAL projects, you have different projects with different capabilities. Today, this afternoon, we're talking about the OP, where we're using the OP5600 because of its EtherCAT capabilities on the Threephase system. So, like I said this morning, we have two proud sponsors for the real-time 2014. We have Threephase and Extend. This morning we did the demo with Extend. This afternoon we're going to do the demo with the Threephase system. So the Threephase system, like I said, is going to be done using EtherCAT communication in a daisy chain fashion to connect the network to the simulator and PHIL simulation. So Pete, if you want to continue.
Okay. What? Yeah. Okay, I prefer this one. So, good afternoon, everybody. My name is Piet van Assen. I'm from the company Threephase. Maybe first a short introduction to what Threephase is doing. Okay, we're actually a small company. We're located in Belgium, near Brussels. Actually, in Belgium, I think everything is near Brussels. And we're active in the areas of rapid control prototyping for power electronics and power systems, on the one hand, and then as a spin-off thereof, we're also active in power hardware in the loop simulations. So if you look at what we do, so we're a company founded in 2006. This is a university spin-off. We currently have a worldwide customer base, although the majority is located in Europe. So our mission is actually to help people that have innovative ideas with regard to new power conversion systems or to new kind of power converters, to help them realize it and test it. So let's say, for example, you have a brilliant idea on a synchro converter, or you want to prototype an 18-phase motor drive. We kind of have the equipment to help you do it, not only in simulation, but also for real. So if the real motor is there and the real grid are there, we are there to help you to make actually the translation from idea to reality. So in a certain sense, we're the next stage when you come from OPAL-RT. The solutions that we have, as I said, are both for rapid control prototyping and for power hardware in the loop testing. Actually, if you look at this at Threephase historically, we started off with the rapid control prototyping problem. We had a lot of people with ideas, but no means to put it to practice. So that's basically when we first developed a platform that coupled a real-time PC-based control target to a number of power stacks. So, and that actually helps people, as I said, yeah, maybe first the application areas, the type of things that our customers do. So people actually come to us for prototyping and testing of motor drives. We also have been active in prototyping hybrid electric vehicles. For example, we have a number of trucks on the road, 20-ton trucks together with Renault trucks and with DAF. That uses our equipment to actually first make the prototype of the electric system. Then we have our power amplifiers, which I will come to. And also, of course, we have there was some major activity, particularly in Europe, with regard to prototyping injection of renewables into the grid stabilization. And we have actually a number of academic and industrial partners who use our equipment to actually, for example, try for real grid support through batteries and stuff like that. So if you look at it from what we do historically, is we started off with a PC-based rapid control prototyping platform to which we could connect a number of power stacks. So instead of working DSP-based like other companies do, we actually chose from the beginning, just like OPAL-RT, to use the power of the PC to actually to manage all possible control loops in our power converters and in our power control systems. So if you, for example, would look at motor drive control prototyping, all control loops, current control loops, voltage control loops would be closed over network with our PC-based unit. In order to help customers then connect their ideas to real power, we actually support and we interface with a number of power stacks that we have agreements with a number of manufacturers, so that actually we can help people that need power in the range from a few kilowatts to a few hundreds to a few kilowatts to a few megawatts to actually get their ideas to actually get the thing going. So to that account, we can actually interface with power stacks from the German company KEB, a number of power stacks from Semicron. We have our own power amplifiers, and then of course we also have a number of current and voltage measurements which you can also connect. Now actually the power amplifiers, the one you see here and the one we actually going to demonstrate, are a kind of a special case. It started off by us using our own power stacks, the power stacks that you see on the left of the screen, and we integrated them with a bunch of magnetics, with a bunch of switches, with a bunch of capacitors to actually make everything you need to generate currents and voltages, to create current and voltage sources. Initially, we actually provided them as completely open hardware platforms, which they still are. So if you buy one, the software is, in principle, you can entirely reprogram it down to PWM level. But we also started delivering software with it, because some customers are not interested in doing all the low-level control loops themselves. They just want to provide a current and a voltage set point and interact in that way with the power hardware. And that's also where the story with OPAL-RT began, because a lot of those people interested in imposing a current or a voltage under a device under test happened to have OPAL-RT simulators. They actually wanted to use the real-time simulation capabilities of the OPAL-RT systems and then actually impose the computed voltages and currents on real devices. And in that case, actually, because you have two powerful PCs in the loop, we actually decided to eliminate one of them, because in that case, customers who do want to do de facto who actually require power amplifier functionality, they are not interested in having those low-level control loops entirely under their own control. So we decided to eliminate our own target in this solution, and we push a part of the software onto the FPGA, which is inside the amplifiers, which normally do nothing from control intelligence, but in this case they do. But the major part of the software goes to the OPAL-RT system. So this is consistent with our philosophy of providing customers open, reprogrammable systems. So even with the OPAL-RT solution, in principle, a lot of the software is still under your control. So you get default software, but in principle, if it would be needed, you could still modify it to suit your needs better. So this gives you actually a solution of reprogrammable power amplifiers and measurements. Let's not forget the measurements, because they're also quite important if you want to make power hardware in the loop simulations. And you can connect it to a powerful simulation unit like the ones that OPAL-RT is actually providing. So this gives you a very powerful solution for power hardware in the loop simulations, whereby a major part of the system that you want to simulate is going to be virtual, so not physically present, entirely in the mind of the computer. And then the three-phase measurements and actuators help you interface with reality, with the device under test, which is physically present. The network technology that we use to interface between OPAL-RT and our power amplifiers is, and there's a word that has disappeared, it should have been Aethernet. Aethernet is actually an open standard field bus technology that allows you to connect a whole bunch of IOs in quite an easy fashion. So you simply daisy chain. So actually, you're going to see an Ethernet wire from the computer to the first device, then a wire from the first device to the second device. So it's a minimal wiring overhead solution. The advantage is also it's very easy to connect a whole bunch of measurements, amplifiers, and also additional I/O to your system and have all the data fed back into your OPAL-RT simulation unit. So you can actually do some interesting data crunching into the inside the simulation unit. So as I said, Threephase delivers 5, 15, and 90 kilowatts power amplifiers, which can be put in parallel if other power is needed. We also provide high-speed current measurements and voltages. Voltage range 0 to 1000 volt, current somewhere up to 450 amps for the moment. And then you can use third-party hardware, for example, like the backup module shown on screen, for all your other needs like analog I/O, digital in and outputs, temperature measurements, getting, for example, a torque sensor inside. That's one of the advantages of using Aethernet. You can really create a real-time data network for which a lot of equipment is already available. So it's quite easy to set up an entire system. What can you do with that entire system? Customers currently have used it for anything. Power grid emulation is very popular, of course. Aircraft grid emulation is a kind of power grid emulation. Currently in aircraft grids you have the 400 Hertz, but you also have the DC networks that are being considered for future aircrafts. Battery testing, motor simulation, a whole range of applications. A little bit about the performance, because it's also often asked. Our products, when actually equipped with the right software, because in principle they're completely open, you can achieve current and voltage step response times in the range 250 to 400 microseconds. That is actually from the start of the set point to the 90% level. If you use 10 to 90%, which is also a common indicator, then you can actually easily subtract 50 microseconds from those figures. But it's not that relevant. If you use them as a 50 Hertz emulation unit, you measure, actually you have measured total harmonic voltage distortion with a Yokogawa power analyzer, and you get 0.05% in steady state for linear loads, being resistive load, and if you connect it with a rectifier and you have some hugely nonlinear load, then the THD performance is still 0.3%. For 400 Hertz grids, the linear and the linear conditions is still around 0.1%, and the nonlinear conditions it's about 1%. So now about the demo case that we are giving. Basically, we have chosen a kind of a visual demo being capacitive discharge through a light bulb. So the device under test is a very sophisticated device that you won't find easily anymore in Europe. It's a traditional light bulb with a based on glowing. And then the emulated system, which is not present, is a capacitor with a resistor and a actually a current source for recharging the capacitor if needed. So if you look on the top figure, to the left is a system being emulated, to the right is a system being physically present. Now, contrary to what is actually common in many power hardware in the loop setups, the simulation does not only contain the virtual part. Actually, we decided to also include a model of the device under test in the simulation. Why? Instead of treating the device under test as something completely unknown, in the simulation we insert the knowledge that we know it is a light bulb. A light bulb is actually a heat varying resistor. So what do? We actually use the measurements that we get from the system to identify actually the characteristics of the light bulb. Those characteristics we use in the real-time simulation. That real-time simulation provides us the voltage, and actually we impose the voltage then through the amplifier on the light bulb. Now, what is the advantage of this approach? If you talk about power hardware in the loop simulation, there's a lot of talk about delays. There's a little bit of delay. There's a round-trip delay between finding out the voltage in your emulation and actually getting back the measurements. Now, one way to get around that delay is, of course, making very, very, very fast interfaces. Ours has a delay of about half a millisecond. Not the communication delay plus the delay of the amplifier. So the total delay is about half a millisecond. But if you use the capability that the simulation is able to look into the future, then you can actually easily bypass the delays that are involved in your amplifier and compensate for other non-idealities of the amplifier by taking it into account into your simulation model. So that's a very easy way, and actually it borrows from the ideas that you have in model-based control. So we make an observer, we actually align the simulation with the measured results, then we simulate a little bit into the future, and that's an easy way to bypass all delays that are involved in our system, and you have a perfectly stable power hardware in the loop solution. Of course, for many cases, in many cases, that won't be relevant because half a millisecond in many cases is if you compare it to the dynamics of the system, it's still small. But if you're pushing things to the limit and the dynamics of your system gets into the range of half a millisecond, then you kind of will get to this solution. Now, it of course perfectly matches with the products of OPAL-RT. The people of OPAL-RT are great in making real-time simulations that accurately predict what's going to happen. So why not use those capabilities, for example, for prediction, for state estimation, actually to align actually those simulations with reality and with real measurements. Next thing is the simulation that maybe. And let's hope. So maybe Carl, you first do your part of the.
So while Pete is preparing the demo, I'm just going to go through the last part of this presentation. So the simulator that is used for the demo is the OP5600. Here you see a wrap-up of the main features of the simulator. So among other things, it contains up to 12 3.3 gigahertz processor. You have also the possibility of a choice between a Spartan 3 or Vertex 6 FPGA board, and access to a variety of IOs. Then if we look closer to the EtherCAT communication, well, basically it works with a single data frame. This means that the same data frame is going to access all the slaves on the system, but every slave has the specific location of the data that it's concerned with in the protocol. We have also we have to note that the OP5600 works as a master, so therefore the 5600 determines what is going to be sent to the other devices on the EtherCAT network. And other things you have to take into account while working with this protocol is that you're going to have a delay of 150 nanoseconds between each EtherCAT terminal you're going to be using. And you can work with a sampling frequency going from 250 microseconds to 100 milliseconds for your simulation in real time. So therefore, the big benefits of using the EtherCAT permits you to drive many devices in a slow loop system that can go in the milliseconds, but also in the hundreds of microseconds. You can have access to a large number of sensors since you can have many devices connected in daisy chain, and you are only using Ethernet cables to make the connections, which make it very simple. So finally, we've been working with Threephase for already 2 years, looking forward to the future, and I think that Pete is going to be ready soon for the demonstration.
Okay, so sorry about the delay. So this is actually the capacitive discharge in the lamp. Can I get, how do you get access to the full model? So, okay. So this is actually how it looks like in the model in actually your in the MATLAB view, actually in the where the model is created. The green blocks have everything to do with let's say managing the EtherCAT master on one hand, retrieving the I/O that comes from the measurements and the amplifier. If you look at the setup, there are actually 3 components. There is the OPAL-RT unit, which is actually being the real-time simulator and also actually part of the amplifier controller. There is the amplifier, which is doing the amplification, which has a small snippet of code for fast local control, and for the remaining part, even the green LED is controlled through the OPAL-RT interface. And then on top, there is the measurement rack for additional measurements. In this case, it's connected to the grid. So this is actually the simulation. This block is part of the amplifier control in the sense that it compensates for amplifier non-idealities. And this is here, the block on top is the actual simulation, the actual model with quite a simple state estimator which estimates the impedance characteristics of the light bulb, which is a heat varying resistor, and then a quite simple network emulation because it is a simple network, so it doesn't require that much. Okay, if we take a look at the results, then here, for example, we see the grid at a time step which is much too large. This is actually the feeding grid measurement. So it's not important for the simulation, of course, but it shows actually yeah, some measurement of a grid you can read into your system. If I connect my PC, you're going to see what a beautiful current is drawn by a modern power supply. So now actually I have connected the power supply of my laptop to the plug, which is actually also measuring the voltages and the currents. So this is simply to demonstrate the measurement rack and how you can actually read the data back into your OPAL-RT system to do something useful with it. For example, looking at the rubbish that your power supply of your PC is generating. On the other side, we have actually the simulation. So this is actually the set point. The yellow, the upper curve is actually the set point which is sent over to the amplifier. That's the purple one is the set point. The yellow one underneath is actually the actual value. And the second axis is the current being drawn. And now you see that's a very, very small current. It's only 0.2 amps. So when the measurement accuracy of the amplifier measurements are in the range 0.05, 0.1 amps. This curve here is actually the conductance, so the inverse of the resistance of the light bulb. You can actually clearly see as the light bulb goes on, the conductance drops, which actually means the lamp heats up, the resistance goes up, so the conductance goes down. And as the light bulb slowly discharges, you see actually the conductance going up again, which means that the resistance is dropping again. So you can actually see and identify the time varying characteristic of your light bulb, and that is, for example, then information you could use through your observer in your system simulation. Okay, and then of course, if you change some parameters, for example, if I make the capacitor somewhat smaller, if I make it 100 microfarad, yeah, okay, it's nicer for the party afterwards. And then you can also see it here on the screen that it goes faster up and down. So, and this is a little bit how you can easily use those amplifiers in creating setups. One of the things to remember is it's quite easy to connect multiple amplifiers because Ethercat is a daisy-chained network. If you would have a bigger rack, next time maybe we can actually install, let's say, 3-4 amplifiers and do more complex stuff. For example, have a complex grid emulator, and at 4 points we have devices under test which are physically present. If you want to, for example, if you want to turn your simulation into a gigantic state observer, you would actually create your simulation, insert multiple measurements in, for example, the system you want to observe, and actually, instead of a simulation only, you actually have you have created a real-time grid observer. Okay, that was it. Thank you very much.
Thank you very much. We have time for 2-3 questions. Yes, I have one.
Hello? Can we go back to slide 12?
Slide 12.
Yeah. Well, there's a like prediction for the compensation of the delay.
Yeah. Here.
So is this automatic? So you have a kind of algorithm to predict this transfer function and to automatic adapt to the system you have. Is that automatic, or it has to be based on trial and error or calculation?
No and yes. The no part is, to be honest, in this demonstration it was inserted manually, but it could actually be automated because the characteristic of the amplifier is known. So, but for the moment it's actually inserted as one of the blocks explicitly in the MATLAB Simulink scheme. Because as I said, in many cases, yeah, this might probably be a little bit overkill. As I said, as long as the dynamics of your system is slow with respect to the delay, basically, yeah, those details don't matter.
Because of a delay, I can understand it can be compensated, but what about a slew rate? So if slew rate the dynamic response. So if we have we use this amplifier as a motor emulator, for example. So if there's a fault or there's a fast dynamic, there's a torque change. So would that be like accurate, can be amplified properly for the response?
The slew rate, when at a given point I gave figures about the dynamics, that is full range dynamics. So anything, when I talked about 250 to 400 microseconds, that's full rate dynamics. That's from minimum negative current to maximum positive current. Anything faster than that, okay, we can give a discussion. It's possible in theory to account for it, but yeah, I mean, then you're again in the real-time simulation model.
Thank you.
Any other questions?
So that is full rate, yeah, it's full maximum dynamics. It's minimum to maximum.
Okay, thank you very much for this very interesting demonstration and presentation.